In the previous session, we have seen the first kind of probability distribution, which was the discrete random variable, the Bernoulli distribution. In this video, we are going to continue into discrete random variable with binomial distribution. So first we'll define it, then we'll go to JASP and understand what are the different options which we have to understand it. So again, defining binomial random variable, how it is important, you already know that if we want to relate it with some actual physical process which is happening in nature or whatever experiments you are doing, and determine that experiment follows what kind of random variables, you need to relate with what is the actual definition of different random variable and which closely fits what are the conditions of your experiment. So we know that the Bernoulli was defined as event which has two possible outcomes and the probability of success should not change. Now in binomial, we have the number of successes in n experiments. So that is how it is going to be defined. The random variable is determining the number of success in n number of experiments. And in Bernoulli, we had only one variable, or in our control, which was the probability of success. Over here in binomial random variable, we have two variables in our hand, or parameters in our hand. The first is the number of experiments we are going to do, and second is the probability of success. So we have introduced one new variable. Now let's come to JASP and we'll continue with whatever we had seen earlier in Bernoulli. So we are using or going to use the same data set which has binomial also, the data points for binomial. So we have 10 data point set, 100 data point set, and 1000 data points in another column. And let's come to so we'll close this Bernoulli over here and go to distributions. So if again the distributions is not seen, go to right corner and check this box. You will find this distribution module and go to binomial now. So again, it has some basic definitions and the standard explanations and standard plot for binomial random variable. So the parameters over here, we have two parameters, the number of trials or number of experiments we are going to do, and the second is the probability of success P. And the number of trials will obviously be 0 to some n number of trials, which will be integers. And the moments are, so from the moment generating function, if we differentiate it for one time with respect to t, so t is one of the parameter we use while getting the value of moment generating function. So moment generating function is derived from summation or integration from some value of 0 to t, and t is some variable over there. And if we differentiate this moment generating function once with respect to t and then put the value of t in that function, whatever we have got is equal to 0, the t value is equal to 0, then we get the e of x, that is the estimated value of x. And if we differentiate it again this value and or the moment generating function with respect to t, and then again put t is equal to 0 in that expression, that will give us e of x square, so estimated value of x square. And we already know that the variance is defined by e of x square minus e of x the whole square, which I have explained earlier also, which is over here. Okay. So this is what we are going to use from moment generating function. Once if we differentiate, we get the value of e of x. If we differentiate twice, we get the value of e of x square. And just doing this calculation, we can get the value of variance of x. So coming back to JASP. So these are the standard, based on the standard data set, which is the ideal data set where the probability of success is 0.5 assumed. And we can close this off everything and use one of the data set which we have. So again, go back and find the correct data set, which is Bernoulli, which has some 10 data points or 100 data points or 1000 data points. So whatever suits you. So more the number of data points, more closely it will be adhering to binomial distribution. So let's just use a data set with 100 and go ahead. So we can get the descriptives, which is what we have studied earlier, the mean, standard deviation, variance, etc., quartiles and all. And we can also determine the first two moments, or first one moment, two moment, any number of moments. So obviously the first moment is exactly equal to the mean. The second moment will be helpful to us to get the value of variance. So if we use this, we can use 31.5 minus 5.35 squared. That is giving me a value of 2.8, and we have the variance very close to 2.8. So I'm getting a value of 2.878, and the variance is very much similar to it. So this may be because of the discrete data points which we have and lesser number of data points. If we have more number of data points, the variance and the variance which we calculated using moment values should come closer. Then we can plot the bar plots. So whatever data points we have, we can plot the bar chart from it. So for a value of 4, there are a repetition such that the probability is close to 0.2, and similarly for different points. And we can also plot cumulative function. So just this probability keeps adding up. The previous probability keeps adding up in the next one. And hence, when we get to the last or the highest value, we'll have the probability density as 1. So that's the definition of cumulative distribution. Then again, going to estimating parameters. So maximum likelihood. Again, we have the maximum likelihood of which is coming up. So the likelihood is 0.535, which is based on the value of n is equal to 10. So we need to change this because we have 100 data points right now. So we can put n is equal to 100, and that will change and bring my p value, which is the significance value, or the mean, which is exactly what we have. So if I that is the probability, obviously. So if what is the probability of getting the success? So it will be very close to 0.0535. That's what we have got over here. Then we can get the standard error in the estimated value of parameter p and the confidence interval. So smaller the confidence interval, I have smaller the range of that interval. Larger the confidence interval, I have more broader interval for that estimated parameter. And the last one is the excess fit. So we can have the QQ plot and PP plot to check how my binomial data set over here is close to normal distribution. And I can use statistic chi-square. So that is because we can evaluate the significance of whatever we have done till now. So the chi-square value based on this data set is coming around 10, and that significance value, so P indicates the significance value, that is based on the value of statistic 10.058. The value is P 0.35. So that's the end over here. And in the next, we'll continue with the next distribution. Thank you.